So my name is Andrew Gross. I'm the Senior Simulation Product Specialist at GoEngineer. We're a reseller in the western half of the United States. And I just have a presentation. Shouldn't take the entire 45 minutes or an hour, maybe about 40 minutes, I think, probably the whole presentation. And it's simplifying complex simulations using virtual materials and connectors. It's kind of a mouthful. So what we're going to look at is just really two scenarios where, using like virtual materials or connectors to really simplify the problem and in some senses be able to solve something that otherwise is really not solvable. So let's go ahead and start. So again, the agenda is we'll look at these smart orthotropic materials and kind of how we're using these for a specific assembly. And we're going to look at determine the fatigue life of springs in assemblies. And we're going to use springs at those connectors, and we're going to go back and forth between using both a real spring, meshing and running a real spring, and then the spring in assembly, and going back and forth depending on which information, what we need from the finite element method. And then we'll do a short question and answer at the end if anyone wants to stick around and ask questions. So let me just talk about the agenda for specifically the smart orthotropic materials. We're going to explore a complex simulation scenario, which initially looks pretty simple, but you'll quickly realize it actually is far more complicated. And we'll determine how to solve that using a simplification technique. We'll create and define an orthotropic material. And we'll incorporate that material into our model, and then we'll, of course, optimize the result, right? Had to throw that in there. So this is sort of the problem we're working on. So just imagine, like a hopper where you have an inlet and outlet for air, and there's some filters and some sprayers and a bowl in this. And what we're really interested in is this filter that lies between the air inlet and the outlet. So that filter is comprised like a sandwich. So we have a bottom kind of a bracing for the screen, and then we have the filter itself. And then on top of that, we have this upper bracing, that's really what we're trying to work on, is to determine we're going to brace the top of this filter to keep it in place and so it doesn't deform or deflect too much when there's a pressure differential across that filter. And in this case, it's a 0.7 psi pressure differential across. Okay? So this is the exploded model. So it seems a pretty simple model on first inspection. So just here's an upper bracing, that's the filter material. This is the entire assembly, so something looks pretty simple. And let's look at, these are just the simple boundary conditions in the loading, right? Very simple. We're just going to fix the edge, we assume that it's welded in place, and there's just going to be a 0.7 psi differential across the filter. So it still looks pretty simple. So the filter itself is 51 inches in diameter, so it's pretty big, right? And we know that there's a bunch of holes, perforated holes, through the filter. And these are on the order of the diameter of about 75 microns, right? So it's a pretty big filter. These are pretty small holes, right? So, 75 microns is about 2.5 thousandths of an inch, right? Really small here. So the surface area of each hole is about 5 times 10 to the minus 6 inches. The surface area of the filter is over 20,000 square inches, right? So if you divide one on the other, well, we've got like over 4 billion holes, right? So you're probably not going to want to model that in SolidWorks, right? Not only will this be a difficult thing to run in a finite element method, but certainly I don't know, you need a cluster computing to really work through all those features, right? So something that's easy, and then you kind of start tearing through it, and you're like, maybe this is not as simple as I thought, right? So how do we model this? How do we model the behavior of this filter without having to punch 4 billion holes in it? I mean, even a symmetry model, right, is still going to have an unreasonable amount of holes, right? The geometry is just, it precludes us from kind of going that method. So we need another method to solve something like this. So if we zoom in at the filter, right, say we take a chunk of it and we pull it out, right, just a block. So we can see a cube that has these holes running through one way, but not the other way. And say it's kind of a regular kind of grid pattern of holes. It doesn't really matter, any type of hole pattern, right? So what we're going to do is we're going to create an orthotropic material that's going to represent the behavior of a filtered material, right? So, just as reference, this is an actual problem that I worked on with a customer of ours. We actually had this problem, actually worked through it, and it matched their bench results. So it's a pretty cool method. So what do we do? So let's start with a block, right? And let's make it easy for ourselves. So we know that these are 75 micron diameter holes. We know that. Okay? And it's a 1 by 1 by 1 block. Like, let's make it easy for ourselves. If we can create the geometry ourselves, I'm going to use the number 1. That's easy, right? Easy to divide, easy to multiply. So let's make it easy. Just a nice little test case. And let's apply a 1 Newton. In this case, we'll call this an axial force, right? Because it's along the axis of the hole. And we're going to determine an effective elastic modulus for this part, right? So that's going to be the effective axial elastic modulus. So what's next, right? So we've determined one direction. Well, now we have to determine the orthogonal direction, right? So this is going to be the radial or transverse elastic modulus, right? Because it's going to be something similar like carbon fiber, right? A transversely isotropic material. Okay? And we determine the hole pattern for the micro model. Right? Again, we know the hole size, and we know the spacing is about 0.15 millimeters. So that's on center spacing. So we want to calculate this effective elastic modulus. So we already know a lot of the stuff we need to determine this calculation, right? We know a lot of it. We know the force. We know the surface area. We already know the stress, right? This is a simple bar example. We already know that the stress is 1 MPa. That's easy, right? What we don't know is we don't know the displacement, right? But we know the characteristic length that we can use to solve that displacement. And then we'll, of course, use that information to determine strain and ultimately the elastic modulus. Okay? So let's get into SolidWorks. Okay. All right. So here's my simple block. So let's, unprepared, I have to add in simulation, right? That's the first thing we always have to do when we're running a study. So let's look at the axial case. So this is made of 316 stainless. Doesn't matter what it's made out of, really, right? Just an example. So to fix it, I chose 3 roller sliders on all the orthogonal planes, right? Because that's going to allow this test specimen to either grow or compress or displace very realistically, right? We're not going to want to fix one side completely or something like that, right? Because we want this thing to move very realistically. Here's my force. Again, this is the axial force. You can see just from the arrows, right? Just 1 Newton. Really simple. And these results take a couple seconds to come up. It's kind of big files. So we can take a quick look at our stress result. But again, we're probably not very interested in that stress result. Right? And we're right around 1 everywhere. What's very important is going to be our displacement in the y direction, right? That's how we're going to determine strain, which is ultimately going to give us our elastic modulus. So not a very commonly used feature, which I use all the time. Has anyone here used list selected? Good. That's like almost half of you guys. That's great. I find a lot of people don't use this list selected, and it's great. Instead of just probing, where it's going to give you just the value at a node, list selected, you can run something like this. Like, I can choose this entire surface, and then when I hit update, it's going to give me a summary, right? So that's going to take all of the nodal displacement on that surface, and it's going to give me an average. Kind of nice, right? If you just click around, you're going to get kind of wild values, but an average is going to be a nice value. For something like this, we want to know what's the average displacement. So in this case, it's 5.9 times 10 to the minus 6 millimeters. It doesn't really matter that much to me. and do the exact same thing in the radial case. In this case, we're looking at displacement in the x direction. Again, it takes a couple secs for this. There we go. We'll do the exact same technique. List selected. Choose the face. Update. And here we have a value of, you can't read it, but I know because that's a 6. So 6.9965, right? Times 10 to the minus 6. Okay. So here we go. So we have our values of displacement, right? And remember, we're using all these ones, so it turns out that our value of displacement, we're just dividing it by 1 millimeter, which same unit. So our displacement and our strain is the same. It's kind of nice. And then our elastic modulus is just the inverse of our strain. So not huge hand calculations here, you know? So what's next? So we've determined the elastic modulus in 2 directions. What else also changes? It's very important, right? We have to calculate the effective Poisson's ratio as well. That's going to be different. So as we know, for really small strain, right, we can approximate Poisson's ratio by the delta L prime, which is right, the orthogonal displacement divided by the load direction displacement, right? So 0.27, that actually is the same as 316 stainless. And that would make sense in the axial direction, right? Because you're not utilizing kind of the change. It's not changing too much the material when you're moving it axially. But in the radial direction, that's where you're going to find it's a lot more compliant, and it could actually behave quite differently. And we see that it does. You know, a difference of 0.27 to 0.23 is actually significant. Okay. So let's go to the model. So like I said, really, really simple model here. And let's look at the setup. First thing, create a new material, right? So copy and paste your 316 stainless. You know, bring it into, you know, our custom material section. And then in our filter, create a new material called filter. And simply, you know, choosing orthotropic as your material type, your model type. And then filling in the values. So in the XY direction, that's going to be the transverse direction, right? They're going to be the same. But the out of plane, Z direction, which we call the axial, that's going to be the one that's different. And then any of the Poisson's ratio with Z in it, right? That's the smaller of the two. That's going to be associated with that radial direction. Okay. And simple contact set, right? And no penetration contact between the bars and the filter. And really simple fixture, just right around the edge. And here we apply our 0.7 psi pressure differential. So this stuff is, you know, this is easy. And from here, we can take a look at a stress value. Okay. So we're making a material that's custom for this, you know, this perforated plate. So I had to throw this in because I'm a big fan of optimization. So this type of model is like a perfect type model for optimization, right? We have a really simple geometry of these bars. What we're really trying to do is trying to determine, let's say, well, what's the bar spacing that's going to be optimum for whatever goal we have? Do you want to minimize displacement? Do you want to minimize stress? You know, so we can easily do that, really easily. And a lot of it has to do with how you've modeled it, right? I mean, if you model something using a lot of parametrics, you can go back and easily change one value and then the whole thing rebuilds, right? So if you look at the model under, okay, where are you? This guy. So if I look at the sketch, the only real thing that I need to adjust here is this 19-inch value, right? Because that's going to, the way I modeled it, the two bars are going to be spaced out. And then I do a circular pattern for the next set of bars. So pretty simple. So if I create an optimization analysis where I'm optimizing that 19-inch value, I can have it spit me out a result that's maybe something that I wouldn't have thought of, or I didn't want to take all the time to check all those different iterations. All right, so let's take a look at the optimization analysis. Very simple again. I like simple. So I just created a variable called spacing. That variable is just that 19-inch dimension. That's it. And I'm saying, well, I want the minimum to be 10 inches and the maximum to be 25 inches, right? Pretty simple. The only requirement you have to have here is that on both the limits, you have to make sure that the model will solve, right? Sometimes you can throw in numbers there that if the model can't solve those dimensions, of course, the optimization analysis won't work. So I chose under constraints, well, I want to monitor both the maximum stress and the maximum displacement. And finally, under goals, well, I just want to minimize displacement. Say for this analysis, I want the filter to just be as minimum as possible, right? I don't want it to deflect too much. So it only takes 3 iterations to run this, because it's only adjusting one value. And it uses the secant method, so it's going to look at the limits. So here's the 10-inch model, right? We know that one's probably not going to be the best. And the 25-inch, also probably not going to be the best scenario. And then it kind of picks one right in the middle. So when it's solved, the optimal dimension is 20.6 inches. And that is going to reduce, it's not a significant reduction. It's less than 5% reduction from the initial, but hey, maybe it's a little bit better. So use optimization. I use it all the time. I think it's great. Okay. So that's it with this example. And I'll stop for maybe if you guys have any questions about this example before I move on to the next one. Cool. All right, let's look at the next example. Okay, so this time we're going to be looking at springs in simulation. So those of you who've used FEA for a long time, right? There are a few big red flags for finite element analysis. One of which, threads, bolt threads, any sort of threads, right? We don't mesh those in an assembly, right? That's why you have things like virtual connectors. And the other one is springs, right? A spring has all of the dimension or all the geometry that is the worst geometry for FEA, right? It's a thin body that turns a lot, which means you can't mesh it as a beam. It's hard to mesh it as a shell. So no matter what, you end up with humongously high mesh count just to mesh the actual spring itself. And that's why SolidWorks simulation has virtual connectors, virtual springs. So you have a spring that's going to behave like a real spring, but you don't have to mesh it, right? So it's really slick. And there are really great ways to kind of have the two play off each other. Either you're running analysis on the actual spring itself, so you're meshing and running the spring, or you're meshing and running the assembly. Okay? So we're going to virtually calculate both the axial and tangential spring stiffness. We'll use virtual springs to determine the deflection of the worst case scenario. And then we'll determine the fatigue life and damage of the springs themselves. So say you're really interested in the fatigue life of the spring. So here are the steps in the process. So like I said, we'll determine the axial and tangential stiffness of the spring. We'll use these calculated values to apply virtual springs to the assembly. So the next question is, well, why are you doing this, right? So maybe give a little background. So say in this shock mount assembly this image of the shock mount assembly, say you have the spring from the manufacturer. Say you have it in your hand. You guys have a bunch of these, but you have no data on the spring at all, right? You don't know the stiffness at all. You know nothing about it. You just know the material it's made out of, and you know the dimensions of the spring. So sometimes that can be problematic. Do you want to test it on a bench? What are you going to do with this thing, right? You don't have any information on it. So even if you don't have information on it, we can use SolidWorks simulation as kind of like a virtual test bed, right? As like we could create like a test to determine that stuff here. So axial and tangential stiffness, use calculated values to apply virtual springs assembly. We'll apply those forces and fixtures to the assembly itself. And the forces are going to be what the actual shock mount's going to be taking on in service. And then we'll determine the actual axial and tangential deflection from the assembly model. And then we'll bring those back to the spring themselves to determine that maximum stress. And then from there, determine the fatigue life if we're interested in, say, it has to go at least 200,000 cycles. Okay? Okay. So this is the shock mount, you know, really simple. So I'm going to go ahead and open up this spring. So these are real simple tests, just like the other analysis, right? We're choosing simple tests. So first thing we'll do is we're going to test for the axial spring stiffness. Simply fix the bottom. We have a 1 millimeter, we're prescribing a 1 millimeter deflection at the top, right? Straight axial. Here's a stress result. We can animate it, right? I use animation not because it looks cool. I mean, it does, but I use it to make sure that, you know, the analysis you're running, is it behaving normally? Is it behaving realistically? Is this what I want? And I can't tell you how many times I've ran an analysis where I've put the boundary conditions and loading, and I hit run, and it's doing something really different that I may have not caught if I didn't animate it. And I'm like, wait, that's wrong. I missed a roller slider boundary condition. I need to go back and rerun this. Right? It happens a lot. Happens a lot. So in this case, right, we're just compressing the spring, you know, one millimeter. Sometimes it takes a second to get out of the animator. So let's find out how much force it took to push it 1 millimeter, right? So that's going to be list result force, right? Great tools here, list result force, right? Contact friction force, also another great tool, works very, very well. So choose a surface, hit update. We're really just interested, in this case, the y direction, right? And y is 23 newtons. So it takes 23 newtons to move 1 millimeter. Again, using really nice numbers like 1, well, that's 23 newtons per millimeter, right? So simple, not much calculation there. Do the exact same thing for the tangential stiffness. Okay, I'll load that, animate it, right? We're just moving it tangentially, no compression at all. Just 1 millimeter in that direction. Okay, we'll choose list result force. Choose that top surface. Again, same thing as before. In this case, we're looking in the z direction. In the z direction, 13.1 newtons. Do you have a question?
How did you restrain that in lateral? When you did the lateral, how did you restrain it to make sure you worked it?
Well, I applied 2 boundary conditions to the top surface. I applied a 1 millimeter tangential displacement and also a roller slider on that flat face. So that keeps the distance straight. You're just moving it laterally, not like this, right? So, and the bottom's fixed. The bottom's fixed. I didn't mention that. If anyone else has a question, sorry, I kind of glazed over those boundary conditions. They're pretty simple, but I'll go back and just show you real quick. So, right, in this case, on that flat face, it's 1 millimeter and 0 normal. So it's just moving, just shifting right across. Okay, so result force, 13.1. Okay, this is what we just calculated, right? So 23 newtons per meter, 13.1 newtons per meter. All right. So now it's time to go back to the assembly, right? And we're going to apply these virtual springs. Okay. So I have a configuration called default with the springs there, but I also created another configuration where I've just created split lines that are going to define the two touching points, right? Split lines, if you guys don't use them or don't know what they are, it is an essential tool for running simulation in SolidWorks, absolutely essential. What it allows you to do is create completely independent faces. So these are now different faces, even though your geometry is not changed, but you're just creating different faces to apply something like this, like in this case, a spring connector. Very, very useful. All right. So in this case, I just fixed the bottom. We're going to assume that this thing is this shock mount of whatever this motor or whatever this thing is, just these shock mounts just fixed right down cemented to the ground or something. We have a force coming on the end of this pin. And we're going to say in the global z direction, we have 115 newtons. And in the global y direction, right, straight down, about 280 newtons. Okay. So let's take a look at a stress result. Okay, so simple stress result. We know that the stress in the top plate, I mean, of course we need to look at this, even though this isn't really this isn't the question we're asking, but it might be useful. We can see we have a safety factor of about 3 there. So we're okay. That top plate, it's not gonna, it can take this load no problem with these springs. But the real important information is determining. So we can see that this spring that's here, right? Oh, not that one, this one. I'll highlight it and then I'll back up so you guys can see what I'm talking about here. The one that has that at that location, this spring in this location is taking the maximum, it's going to take the maximum amount of deflection, right? Because of the direction of the loading, it's going to be squished the most and it's going to have the most tangential deflection as well, right? And we can see that even easier when we look at an exaggerated displacement result. That's where most of the stuff's happening there. So that's where I meant worst case scenario is going to be that spring right there. The other ones are going to be in a easier spot. This guy is going to take on the most. So that's really what we're interested in here. So we want to determine the displacement in both the y and the z direction at that spring location. So let's go to our displacement. This is our y displacement. In this case, I can probe it, and I use split lines so I could get a vertex at the center of that spring. Okay, I use split lines there. And we can see that the y displacement here is about minus 2.03 millimeters. And we'll do the same with the z displacement. Oops. Probe first. 1.1 millimeters, right? So what's the game plan now? So we've modeled the assembly with the virtual springs. Well, now we have to apply these displacements back on the spring model itself, right? And we can use that same model that we used to determine the stiffness. Oops. So let's go back there. Okay, back to this model. Just have this one called maximum displacement. Again, really simple. This is a plain carbon steel spring, totally fixed the bottom. But now on the on-flat faces boundary condition, 1.1 millimeters lateral, right? 2.02, I thought it said 3, maybe that was a typo when I ran this. 2.02 millimeters axial, right? And this runs very quickly. So now let's take a look at stress. We can animate this again to make sure it's behaving the way we expect it to. Okay, that looks good, right? Mostly compressing, but a little bit of, parallelogramming, you can say. And we can immediately see the location of maximum stress, which is kind of what we would expect, right? Near the ends. So from here, we're just going to create a fatigue analysis using this static analysis, right? Okay, so fatigue analysis. I know that this is carbon steel, so I can choose to have this based on the ASME carbon steel curve. This is a nice tool that a lot of people don't use as well. It's really nice if you don't have an SN curve for something that falls into either ASME carbon or ASME austenitic steel. You can use these to estimate an SN curve. Steels tend to behave pretty similar. I have seen people try to use these for aluminum. I would not suggest that. I actually have seen that. I have seen that. So don't do that, please. Aluminum doesn't behave anything like steel. Okay. Anyone here ran a fatigue analysis in SolidWorks simulation? 1, 2.5. Okay, okay, no, that's good. It's really simple. Really simple. You create a new study, you give it a material, now an event. You create an event, right? This event is going to say 200,000 times. We're going to take this study that I ran, this one maximum displacement, we're going to run that 200,000 times. And in this case, it's going to be a zero-based analysis. We also have other choices here. And that's it. So now we can see results for damage. So in this case, right where we have maximum stress, we can see that that's 200,000. We're going to have damage of about 51.5%. So we're safe. We're good. Safety factor almost of 2. And life. Life is just going to be the cycles to failure, right? So at these locations of maximum stress, we're seeing about 388,000 cycles to failure. So we've passed, right? Okay, so just a couple slides what we just saw, right? So we determined the actual deflection of the spring. I say actual because I plugged in the values of that virtual spring that we solved for. We can see maximum axial displacement, minus 2.03, tangential, 1.11. And we use that to get our fatigue life and damage of the spring, right? It's pretty simple. So that's it. I'm just going to go through a recap, and then we'll do some questions and questions if you guys have any. So we looked at the smart orthogonal materials, right? And how we did that is we virtually tested a micro sample of the material, right? So it behaves like, it's essentially one homogeneous material that behaves like something that maybe geometrically is a little different, but we're utilizing the symmetry or the the regular patternness of the geometry. Right, what I just said. So we solved the problem and we optimized the result. In the spring simulation, right, we virtually tested the spring stiffness. We applied the virtual spring to the assembly, right? We then solved for the maximum deflection of the spring in the shock mount, and then we used those maximum deflections to go back and determine the fatigue the maximum stress and fatigue life of the spring itself. Okay, are there any questions? Okay, so I'll be here if anyone wants to ask me questions afterwards. I really want to highlight again, I really appreciate you guys all coming out. I know this is the toughest time to come out, but this is great. This is great. Thank you guys. And once again, my name is Andrew Gross. I work at Go Engineer. It's my email address. Let me know if you guys have any questions later. I'd be happy to talk to any of you guys. So thank you again.